Hi class, we are on the last section of chapter 2, section 2.5. This is the epsilon-delta definition of a limit. So this is the formal definition of a limit. This is something that you'll see obviously in Calculus 1. Then you probably won't see it again unless you're a math major when you study a course like rule analysis. So in this section what we're going to do is we're going to get into a very rigorous definition. You'll probably see your first real proof. So we'll have, some proofy type things, which is something that we do a lot in higher level mathematics. Okay. So in a standard textbook, you'll see proofs everywhere in a calculus course. In this class, you'll see them every so often. When we talk about the intermediate value theorem, that's somewhere where proofs may kind of creep in. But this is going to be our first real formal proof that we'll see. For those who are taking my class, not just watching this on the internet, I'm not going to have you actually prove anything. This is really just for us to get a better understanding of what a limit is. And for those of you who are math majors or physics majors, this will help a lot in their studies later on, getting this sort of rigorous exposure here for mathematics. So let's talk about our definition. Okay. So let f be a function that's defined on an open interval. Okay. And let's say that this open interval contains a value a, the x value, right? Typically this value a is the value that we're approaching for our limit, right? So this is an input value. Let's say that our function is or is not defined at a, right? So think about a hole. So a could be where a hole in our graph is located, or it could be continuous. It doesn't matter, right? Because for limits, remember, we don't have to actually exist at that point. We just can't have a jump discontinuity or a vertical asymptote. Okay, but a hole or actually being defined at this point is fine because the left and the right side limits agree with each other. So for definition of a limit, we don't have to exist at a, but we have to be defined around a, basically. So what we say then, as we've said before, is that the limit of our function, f of x, as x approaches this value a, is the value L. And the way that we write this is the limit as x goes to a, f of x is L. So we've seen this quite a bit already. So this notation and this verbiage isn't new, but the way that we describe this rigorously will be. All right. So the definition goes that if, and this symbol means for every, right? So for every epsilon that's positive, larger than 0, so this means that any choice for the value epsilon that I can think of, there exists, this backwards e means there exists a delta that is larger than 0, such that if the distance between x and a, so any other point, and our value of a that we're approaching for our limit is less than this value of delta, then the distance between the outputs are less than our choice of epsilon. So I'm choosing an epsilon, and I say for whatever distance, I could say that this is, we typically use small values for these because again, we want to get really close to a. So what I'm saying is that if I have, I don't know, let's say that epsilon is 1/2. If I want to make sure that the distance between my function outputs and a limit is less than 1/2, then there exists a value such that the distance between my inputs required for this distance is always going to be less than that value. Okay, so it's really much easier to see when we have a graph. So we're going to have a function f of x. Okay, I have my limit that I'm approaching for my inputs of a. The output there is L, right? Or the limit is L, I should say, because it's possible there's a hole here. Now, if I look within an interval around a, within the neighborhood of a, that is within the distance of delta, then my outputs are going to be within a neighborhood of epsilon away from the limit. Okay, so that's basically what this rigorous definition is saying. So as long as I'm plugging in values, if I want to be within a certain tolerance around my limit, then there's going to exist some value of delta such that all of my inputs will give me outputs around that value of L. Okay, so this means that no matter how close we want to get to our output, L, our limit, so within a distance of epsilon, that we can find a value of x that's close to A, and it is within a distance of delta. Okay, so let's go ahead and do an example. So let my function be this piecewise function. Okay, so it should be very clear here that the left and right hand limits agree at x equals -2, but my function is not the same output, right? If I was to plug in -2 here, I would get out 4 minus 1 is 3. But I'm saying that there's a hole, there's a jump discontinuity. So instead of having 3 as the output, I'm having 0 as the output. So we want to know how close does my inputs need to be to this value of -2 for my outputs to be within a distance of 0.01 from 3, what I'm supposed to be at, the limit as I get close to -2. So basically what it's telling me here is it is giving me an epsilon, right? This is the distance I want to be away from the limit value at -2. So the limit of this function as x goes to -2 is 3, because from the left and the right side we approach 3 here, right? Because it's a hole, not a vertical asymptote. So if I want to stay within 0.01 from 3, how far away can I travel away from -2 to make sure that I stay within 0.01 to 3 for the outputs? So how far away can I travel from my inputs to stay this close to my limit value of 3? Okay, so we're given an epsilon value, we're being asked for a delta value, right? So again, note that there's a jump discontinuity here at x equals -2. And so the limit as I approach from the left side of my function is the same as the limit as I approach from the right side, which is 3 in this case. Okay, so I can plug this in and I just get 3 from my limit. Okay, so using the precise definition for our limit, we can figure out what the delta needs to be, right? So I know that my value of A is -2. So if we just go back real quick, we're going to use all of this information here, right? I'm given an epsilon, it's 0.01. I need to find my delta. I know A is -2, and I know my L is 3. So I can just plug all the stuff in that I need here, and then just try to wiggle my way to get to a correct answer. Okay, I know what my function is, I know what my limit is, I know my epsilon, I know my A, I don't have a value for x. X is going to remain as a variable. This delta is really what I'm trying to figure out. Okay, so come back here. Right, so we have A is -2. My limit I know is 3 because the left and right sides of this agree. So it's pretty much just like if I were to plug in -2 to this regular function, because I created a jump discontinuity there. My epsilon is 0.01. And so when I start to plug things in, this is kind of what it looks like, right? So I need my function minus 3, right? The function minus the limit to be within a distance of 0.01, top or bottom. If I'm plugging in values around -2, those values that I'm plugging in have to be less than this distance away from -2. Okay. So simplifying this, I get x plus 2 is less than delta, which implies, okay, let's go back a little bit. Absolute value means that this whole thing on the inside is either positive or negative because it's absolute value. So I can break this down into 2 equalities. So my 2 equalities are negative delta minus 2 and delta plus 2. So basically what I'm doing is I'm taking if this whole thing is positive or if this whole thing is negative, and then I'm just isolating the x on the inside, right? So it has to be within the distance of 2. So x is delta plus 2, or it is negative delta minus 2. So here I have that negative delta minus 4 is less than x minus 2, which is less than delta. So what I did here to get to this line is I subtracted 2 from everything, right? This whole inequality I subtracted 2 from. So if I subtract 2 from this side, I get negative delta minus 4. If I subtract 2 from x, I get x minus 2. If I subtract 2 from here, I get delta. Now you might say, Professor Williams, why the hell did you subtract 2? What does that do for us, right? I don't see why I would need to do that. The answer is because I did some work on the side, some scratch work, and I know that I need to have x minus 2 for what's coming up next. And so I need to have a relationship using x minus 2. So the reason that I'm doing this is basically because I'm going to need it in a couple more steps ahead. And so in order to make this work, sometimes you have to go ahead of yourself and figure out what it is that I need. Okay. So you're probably saying that's a terrible answer, but it's okay. Just stick with me and I'll circle back to this point once we see it, and you'll see why I needed x minus 2. Okay. So really what I'm doing here is I'm building a relationship with x minus 2 and delta. Okay. So x minus 2 is less than delta. X minus 2 is more than negative delta minus 4. So I know that the absolute value of this, okay, is going to be less than delta plus 4. Now, why is this useful? Because it is. Because really what I need is this x minus 2 and its relationship to delta. Okay. So x minus 2 is not less than delta, but it is less than delta plus 4. So where did the delta plus 4 come from? It comes from this inequality. If I take the absolute value of this, of negative delta minus 4, and I absolute value it, it'll become positive. It makes delta and 4 positive, basically, right? That's the distance I am away from x minus 2. So absolute value wise, if this is less than delta, then this has to be less than delta plus 4. Okay? Because, right, the absolute value of negative delta minus 4 is larger than delta is, right? Because it's delta plus 4 away. So here, this is why this stuff gets tricky, because we're always dealing with inequalities. Well, this is less than this is less than this, or this is more than that, which is more than that. And that's how we really work with these types of epsilon-delta proofs, right? These formal definitions. It's all about, well, this is less than this, and this is less than that. So we really just have to build these relationships. I know that the absolute value of this is larger than delta, because the absolute value of this is delta plus 4, right? If I took negative 3 minus 4, that's negative 7. That's a value of 7. So I can just take this value and make it positive, and I know that this is larger than delta, and x minus 2 is less than delta. So if this is less than delta, then it has to be less than delta plus 4. Okay. And so I'm really just using the left side of this inequality, taking its absolute value to give me my bounds. So what I'm doing is I'm choosing the largest of the two, right? Away from x minus 2, this is the larger boundary. This is the larger bounds. This is larger than this if I took it for just its value, how far away it is. This one is larger, so that's why I'm taking the absolute value of x minus 2 and I relate it to whichever side is larger in value, right? Absolute value wise. Now, if we come back to what we were doing, okay, so this is me working my this part, the absolute value of x minus 2 being larger than delta. So I worked this down to something that I'm going to need. It's no longer x minus 2 and it's turned into x plus 2, which is fine because now I have a relationship for x minus 2 and a relationship for x plus 2, which only for this example is what I need. So we're going to start working now with my function minus my limit being less than 0.01. So now we're going to switch gears and we're going to focus on the function and its limit instead of the input and the input value for my limit. All right. So I have my function x squared minus 1 minus 3. So the function minus the limit. If I simplify this, I get x squared minus 4. So now do you see why I needed an x plus 2? I needed an x minus 2 because I already had an x plus 2. Okay, I already had x plus 2 from x minus a, but I also need x minus 2 because when I put these two things together, I get what happens when I have my function minus my limit, which is x squared minus 4. So what I can do is, now that I have my function minus my limit, I can factor this, and I can take the absolute value of each factor. Okay. So the absolute value, the distance between my function and its limit, is the same as x minus 2, the distance of x minus 2 times the distance of x plus 2, which is less than epsilon. So I have my function is less than my epsilon. And now I can relate these things to some deltas, because I know x plus 2 is less than delta. Okay, x plus 2 is less than delta. And I know x minus 2 is less than delta plus 4. That's the reason I have this. Okay, so if I make those relationships, x minus 2 is less than delta plus 4. X plus 2 is delta. So this whole thing is less than these values. Okay, which has to be less than 0.01. Because I know x minus 2 is less than this, and x plus 2 is less than this, and the product of these is less than my epsilon, so I need this relationship of my deltas to be less than 0.01. Okay, so now I can solve this and I can get the values of delta that I need. So this is how I'm singling out my deltas, by making these relationships. Okay, so if we solve this inequality that we have, so again we need this to be less than 0, we're going to get these two values, right? So we'll get obviously I shortcutted the work, right? But the exact values that we have, the decimal approximations, are as follows. Okay, so since we're using epsilon and deltas, we're using decimals here. Okay, the exact values are 1/10 square root 401 minus 2 as the exact value, right? So really absolute value this, so plus and minus on both sides. So if I come back, the value of delta that I need is this value, and since delta has to be 0, that means we're sticking with this positive value, right? So this has to be less than 0. So let's come back up here real fast. Okay, the condition is for every epsilon I choose, in this case 0.01, there is a delta that's larger than 0. So I solve for my deltas, and one was positive, one was negative. I have to use the positive one. Okay, so let's come back here. So I have to use the positive one. So delta is less than 0.002498. I didn't write it, but it's given that it's also larger than 0. Okay, because that's the condition. So the value of this one, the exact value, is 1/10 times square root of 401 minus 2. So that's the exact value of delta that I need. Okay, so we don't, that's very confusing, so we can just give our decimal approximation. Okay, so let's say we wanted to prove this for any choice of epsilon. So here I gave you a very specific value of epsilon, 0.01. So how would I say this for any epsilon, right? So proving this for any epsilon is how I prove that this limit exists. So notice that if we restrict x plus 2 to be less than 1, since we need this to be small, we could just say let it be less than 1. Then we would have the following. Okay, so I need this to be less than 1, so absolute value means it's less than 1 and negative 1. Subtract 2 on both sides. X has to be between negative 3 and negative 1. And then when I subtract 2 to get my, because remember I need my x plus 2 and I need an x minus 2, I now have x minus 2 is bound between negative 5 and negative 3, right? So therefore, choosing the largest side, the absolute value of x minus 2 has to be less than 5. Okay, so this implies that the absolute value of x minus 2 times x plus 2, as we saw from up here, being less than 0.01 means that I have 5, because x minus 2 has to be less than 5, times x plus 2. I don't have a bounds yet for x plus 2. Not in terms of delta, I don't. Right? I'm saying it has to be small, it has to be less than 1, but I'm not restricting this yet to say, oh, this is 1. So x plus 2, if I solve for this, has to be less than 0.01 divided by 5, which is 0.002. which is less than what we came up for epsilon being 0.01, right? So it agrees with my impromptu example. So before we go to the next example, let's look at this a little bit. Okay, so for this one, I'm actually going to keep the work that we're doing on the side visible for you. Here we're playing around in Desmos, as always. So here I have my function. I have it's discontinuous at -2. Actually, I have to put the bounds on that. It doesn't really matter, but so x less than -2, x larger than -2. Okay, there we go. So I'm undefined at -2. Okay, and you can see here that I have -2, 0 as the point. So there's a removable discontinuity. It's just a small jump here, right? So this is not jump discontinuous because yeah, it jumps in value, but my function continues on in the same place. So it's just a hole. It's a removable discontinuity because I could put this point back, right? And it would be continuous. So what I'm going to do is I'm going to have a line. This is my x value plus my delta. So if you remember what my delta was, it was 0.0024984. Okay. So if you see, it looks like it's exactly on the line. So I'm going to go plus that amount and minus that amount. So if I were to zoom in, you would see that it's actually an interval, right? It's very, very small, but it's still around my values. Okay. So again, we want these things to be very, very small. So at my value of -2, my point of interest and my limit, there we go, I am very, very close to it. Okay. And so then what we're going to do is we are going to look at my outputs of y. Okay. I want to be around my output value of 3, my limit of 3, and I want to be within 0.01. So I'll put a line above and a line below. So now I have crosshairs, basically. Okay. So I have a little bit of space that I'm working in. Oops, here we are. Okay. So this is my value, my limit that's undefined. Okay, it should be -2,3, but as you can see here, it's undefined. Okay, this is my line, -1.996, so it's -2 plus, so this is the upper bound. So this is my x value, my a value, plus delta, right? This is my x, my a, minus delta. Okay, this is my limit of 3 plus epsilon and minus epsilon. So now if I make my point exist, I don't have to label it. Okay, and notice here that I'm saying for my point A, let's stay within my boundaries. So my lower bounds is -2 plus my delta. Okay, so that's why you see it's -9975016 is the same thing here for -2 plus my boundary. And so here you look, I have my A value, which is on a slider, and the output. So this is going into my function, right? So remember what we want for limit. We say as long as I'm close within delta, right, from x, so within these boundaries of plus delta and minus delta, which I have my A value plus delta, my A value minus delta. So I'm calling it A here because it doesn't really matter. I can call this B. I'll leave it alone, but it could be B. I should stay output wise, my outputs should stay within epsilon of my limit. Okay, so if I run this on a slider, you see I never go outside. As long as I'm staying within delta of my limit as x goes to a, my outputs stay within epsilon of my limit of 3. Right? And it's that exact value that I calculated, 0.002498. It never goes outside of this box. Right? So that's what we proved. Now, if I chose a different value for this, I would have to have a different boundary for this box on the left and right sides. Right? So if I chose a different height for the boundary on the top and the bottom, I'd have a different lengthwise on the boundary box, and I have to recalculate that over and over again. So that's really what we just did here, is we said as long as I'm within a certain distance of the limit I'm trying to approach, my outputs will always stay within this distance of my outputs, right? And those values, as you can see, are very, very small, right? So if I come out, you're not even going to be able to tell that anything's actually happening, okay? And so the definition of a limit is I could choose how small I want to get. This distance of epsilon away, I can get as close as I want. I can make this 3 plus 0.00000000001, and I could still find a delta, a distance away from this value of -2 that will still make that little animation that I did work. Let's do another example. So for square functions, we needed to have those two pieces, right? Because when I plug in my f of x minus my limit, I get another quadratic that then would have to be factored. So I needed those two different pieces. That's why I needed to do all that work for this x minus 2 part. Because I knew already x plus 2 was less than delta, but I didn't have any relationship for x minus 2. And then I just kind of did it over again, but with the generic value of epsilon here, right? So for this example, we will do the same thing, but we're going to prove it in general, right? So here I didn't really prove it in general, but I did just say, hey, notice that if I restrict this epsilon to be even larger, I'm still within a distance of delta, right? So now we're going to do it in general. You've seen how it works already. I showed you kind of how I would need to find some scratch work in order to make this all come together. So if we do an actual proof, this is what it will look like. Okay, so everything will be generalized here instead of static values. So here, let epsilon and delta both be positive values. Okay, I need x plus 2 to be positive and less than delta, right? I haven't chosen a value of delta yet because I don't have an actual value for epsilon. These are generic values right now, right? I'm going to say let delta be the minimum of 1 and epsilon over 5, or 1/5 of epsilon. Whatever it is epsilon ends up being. How do I know I need 1/5? Because of this scratch work here. I said let it be 1, and then I was like, hey, well, what happens when it's 1? I get a 5 here, right? And I ended up having to divide by 5. So this epsilon divided by 5 is what ended up happening. So what happens if it's any epsilon and not just 1? So that's why I'm going to say let it be 1 or let it be epsilon divided by 5. Let it be those two choices. So let's say that delta is 1. Then the distance between my function and the limit of my function is x squared minus 1 minus 3, which we've seen already, which I can then rewrite as the absolute value of x squared minus 4, which I can break down to x minus 2 times x plus 2, which then I can then separate into two separate absolute values because it's a product of factors. I know that this is x minus 2, okay, because x plus 2 is less than 1, right, because I chose that. X plus 2 here is less than delta. If delta is 1, then a small number times a large number times anything is always smaller, right? 1/2 times 5 is something smaller than 5. So if I take off the small number because it's less than 1, x plus 2 is less than delta, which means that if delta is 1, x plus 2 is less than 1. So it's a small value, it's larger than 0, less than 1. If I multiply that times something, it's going to be smaller than the original. So I can say this whole thing is less than if I took off the small part that's being multiplied. And that has to be less than 5. Okay. So if I wrote this as an inequality, we know that x minus 2 is less than 5, right? I get plus 2 and minus 2 on both sides. That distance is a distance of 4, right? From -2 to 2, that's a distance of 4. So I bounded it by the value of 5, right? I know that this is a true statement. X minus 2 has to be less than 5. It has a distance of 4, so I know that, right? 5 is going to be less than epsilon, okay? And I know that's true because epsilon over 5 is less than, it's going to be greater than 1. How do I know it's greater than 1? Because I'm saying it's greater than 5, right? So 5 is going to be less than epsilon. So therefore, the distance between my function and its limit is less than epsilon if delta is less than 1, right? Now, if delta is epsilon over 5, we kind of do the same thing. My function minus my limit is the same as x squared minus 1 minus 3, or x squared minus 4, breaking it into pieces, okay? So here, I know x minus 2 is 5. I know x plus 2 is less than epsilon minus 5, because that's delta. Here I'm choosing delta is epsilon over 5 for x plus 2. X minus 2 we already know is less than 5. So I got this is less than 5. This is less than epsilon over 5, which means that this is less than epsilon. So I have my function minus my limit is less than epsilon if delta is epsilon over 5. Right? Therefore, if my distance between x and negative 2 is less than delta, then the distance between my function and its limit is less than epsilon. So basically what I did is I showed it for two parts. I showed it for, I had two different choices, either epsilon over 5 or 1. And I showed that if I choose 1, that everything works out. And then I said, well, what happens when I choose the other one instead, epsilon over 5? Well, if I choose epsilon over 5, it also works because if this one is smaller than 1, I already know what happens when it's 1, right? So I know that when it's 1, that x plus 2, that x minus 2 has to be less than 5. Actually, I don't even need that part. I know x minus 2 is always less than 5 because of the reason that we said here, right? I know the distance, this is always 4, right? So I put a bounds on it. Okay, now, if you're like, Professor Williams, what the hell? I don't understand anything that just happened. That's fine. I just need you to understand the first half, and then I'm showing you, hopefully you'll pick it up. But again, I'm not going to ask you to prove this stuff, right? But I do want you to see how higher level math works. Okay, this is generally what we do once we get past things like differential equations or calculus 3. Our math starts to look more like this than it does adding and subtracting and multiplying a bunch of stuff, right? So let's do one more example. We'll do a limit proof for a linear function for a line. It's much simpler to do and easier to understand than it is for a quadratic. For a quadratic, I'd have the two values, and that's because x squares can do a whole lot of stuff, right? So I have more things going on. So let's go ahead and prove that the limit for 3x minus 1, or sorry, 3x minus 4 as x goes to 1 is negative 1. So that we can see here, we have a line. Line is continuous. So if we plug in 1, it's very easy to see that the limit is negative 1. But how do we prove that, right? So we're going to do the same thing. We need an epsilon. We need a delta. We need them both to be larger than 0. I need to look at my function minus its limit being less than delta. Now, real quick, we always choose our delta to be in terms of epsilon. The only time we don't here is, for quadratics, we kind of give it a choice. We have a 1 and then some relationship with epsilon. So what we had over here for the last one is this is what the side work would kind of look like. I said let it be less than 1, and I came up with a relationship, and then in the end you see the relationship here, my choice of epsilon being less than 5, right? So that's why I had the choice of 1 or epsilon less than 5. But then I did it in general, and I didn't say this value of epsilon, I said any epsilon. And that's the way that it worked for this example, for my choices. For a line, you don't need choices, right? You would do some side work like this in order to figure it out, but we don't need two cases for that. So, okay, I'm going to start off the same way. I need epsilon and delta. I need them larger than 0. I need x minus my limit value, my a, right, that I'm approaching to be less than some value of delta. I would like to rewrite delta in terms of epsilon. So I would do some scratch work in order to figure out what that relationship would need to be. like this. I had epsilon over 5, right? In order to figure that out, I went over here and I did some side work, right? That's how I figured out that, that's how I figured out I needed it to be less than 5. Okay, so, or divided by 5, I should say. Alright, so I'm going to have epsilon over 3 as my choice. How did I know that I needed it to be epsilon over 3? Again, I did some work on the side, okay, that you haven't seen here. So now I need my function minus my limit to be less than epsilon. So let's plug that stuff in. I get 3x minus 4 minus a minus 1. So I get 3x minus 3. You see what that scratch work was? Okay, I plug the stuff into here and I set it equal. I set it less than epsilon, and then I said, hey, that's what I need. So here I have 3x minus 3. I can pull out that common value of 3. Okay, so far it's all equal, no inequalities yet. That would be the same thing as 3 being less than epsilon over 3, because what do I have? X minus 1. That's not a coincidence. It should pretty much always happen that what I have here being less than delta happens when I plug in my function minus my limit, and then I simplify it. So I have 3 times my distance that I have that needs to be less than delta. Delta written in terms of epsilon, so that I can have this relationship, right? 3 times my thing that's less than delta. So then 3 is less than delta, which simplifies to be epsilon. Okay, so therefore the distance between my function and its limit is less than any choice of epsilon if my x values that I'm plugging in are close to my limit that I want to approach within a tolerance of delta. Okay, therefore the limit of x goes to 1 for 3x minus 4 equals negative 1. You see how this is very, very short and simple and to the point. I didn't have to have several choices here, and that's because it's not a square function, so it makes it a lot easier to write a proof for something like this. Again, I don't need you guys to write proofs in this class for limits, for epsilon delta limits. They're difficult. Every time I go over this in my classes, I have to review myself because it's hard for me also. But I want you, my expectations for you, at least moving past this, is to understand how to find your choice of delta. Okay. Now, whether or not you calculate this by yourself or you play around on Desmos and figure out what that value needs to be just by playing around, that's good enough for me. So most of your problems that you're going to run into in this class are going to be something more like this first portion of it, or just understanding kind of what it is that we're trying to do, that we're trying to stay within a distance. I have a choice of the tolerance I want to be around for my limit, which means that I will always be able to find a boundary for the values that I need to plug in for my values close to A. Okay, that's really all I need for you guys. So that's it for this section. Hope this was helpful. If you need to watch it again, then feel free.